Jorge Diaz is a Chilean physicist. He studied at the Universidad Católica de Chile, where he got his bachelor in science. And then he moved to Indiana University, where he got his master and doctor of philosophy degrees in theoretical physics. After that, he got a postdoctoral position at the Karlsruhe Institute of Technology in Germany in the area of astroparticle physics. And I would say, unfortunately, he moved then out of a university. He moved to SAP as a machine learning engineer, and now is research scientist in BASF. But he is still with us. He is a visitor scholar at Indiana University, Bloomington. So we are happy to have with us today Jorge Diaz. He will talk about blast wave kinematics, theory, experiments, and applications. Thank you very much for being with us. Dale nomás.
Okay, so yeah, thank you, Lautaro, for that nice introduction, for the opportunity to share this this work here. Yeah, as you say, I moved to industry a few years ago, but I keep doing physics just for fun. So this is what I do on my free time. I guess different people have different hobbies. So I would like to talk to you today about a work that I started last year out of complete ignorance. Basically, I'm not an expert on many of the things that I will talk to you today, and so I learned a lot in the process. So most of the content will be based on this paper released on the archive just last month. So I would like to get started with a little disclaimer. I don't know anything about explosives. I'm not an explosives expert. I have no knowledge on how to do any of these things. All what is shown here is public and for academic purposes only. And since I will show a few images of the tragic explosion that took place in Beirut last year, I also express my sympathies and appreciate many of the material that has been available. So with that said, the outline is quite simple. I would like to introduce the topic of explosions in general from a physical point of view. I will show you some images, some short videos on how this got started, but the main goal is the midpoint, which is the physics of explosions. I would like to show you how to find a relation of position versus time of an explosion so that we can learn about it by measurements, because measuring position versus time is something that we learn in our first year in physics. So being able to learn about something as complex as an explosion out of this very simple kind of measurement is, I find it of interest. And I will show you experiments and applications of what we found. So to get started, one of my favorite experiments in the history of physics, it had very tragic consequences. I cannot deny that. But the Trinity test, this is the test of the first nuclear weapon in 1945, is what somehow got me started in physics when I was a kid. So I've been obsessed with this for many years. You can see here the device it has this spherical shape, which explains the name of this design is called Fat Man for obvious reasons. If you're curious of the size, you can see people standing next to it. It's really big, but you can see this little black cylinder shown there in that image. That gives you an idea of how big the plutonium core is. It's about the size of an orange. So it's really tiny. In the early morning of July 16 of 1945, this device was tested, and there are many pictures of it. I'm pretty sure you have seen many of these pictures. What is shown here is these are timeframes or screenshots, if you want, of high-speed cameras at different times. So these are a few milliseconds after the explosion, all the way to a few seconds after that. And we see the classic mushroom cloud. The reason this is relevant for this discussion is because of the participation of this gentleman here. If you're not in the field of fluid dynamics, you might not have heard his name. If you are, you know that he's one of the heroes of hydrodynamics in general of the last century. Geoffrey Taylor was a British mathematician and physicist. If you Google his name, you'll find that, or you check the Wikipedia entry, you'll find there is a dozen things named after him. What I'm showing you here on the right is the first page of a paper that he wrote, as he says on the first line, in 1941. So this was a top secret document for almost a decade, was finally published in 1950. And what he derived was his formula shown at the bottom. So it's not very clear, so I render it. So you can see this is a formula that tells you the size or the radius of a sphere. It's basically the explosion, the blast wave, in terms of physical quantities, in this case, meaning the time, the energy of the explosion, and properties of the medium. If you just Google the story of Taylor, you will find immediately many discussions about the use of dimensional analysis to derive this formula. And that is something that he did. There are a few assumptions that you need to make. So what Taylor did was he considered the explosion to be spherically symmetric, because cows are spherical, so of course explosions are also spherical. That simplifies the equations dramatically. He assumes that the energy is released instantaneously and from a point, which is quite valid for a nuclear explosion, not very valid for all chemical explosions though. He also assumed that the pressure inside the blast wave, so the pressure inside this volume, is very large compared to the pressure outside this region. So P0 will be just the atmospheric pressure, rho 0 is the atmospheric density, and this assumption is going to be extremely important for what we will do next. There is this big jump in pressure right at the boundary of this sphere. And he described the gas as an ideal gas, of course, and is completely characterized by the heat capacity ratio, gamma. So what you get out of these assumptions is when you use conservation laws, conservation of energy, conservation of momentum, conservation of mass, you find that there is a set of relations at the boundary. So when you study the propagation of this shock wave, there are some boundary conditions which are known as the Rankine-Hugonot relations or conditions. It's just the boundary conditions at the boundary, as the name indicates. But then one thing that he did was, what are the independent physical quantities? So how can I characterize this? So one thing is the radius, of course, that quantifies the size of the explosion. Gamma tells me about the thermodynamics of the gas. E0 is, of course, the energy that is released. And then you could say, well, where is the pressure? Pressure and density are not independent because they're related via the equation of state of the gas. And as I mentioned, these boundary conditions allow me to relate the quantities inside and outside. So out of these four variables, P, rho, P0, and rho 0, I only need one of them. And that is what is shown here. The variable selected was just rho 0, so the density, and T is the time, so we can study the time evolution. And this is the exercise of dimensional analysis, is that you can write down a general formula as a power law of each of these variables. And here S of gamma is just a arbitrary function and dimensionless function of the heat capacity ratio. And if now we look at the physical dimensions, that means mass, length, and time of each of these variables, and we put them together and we impose that this formula is dimensionally consistent, what we find is a system of three linear equations with three unknowns. So solving this is a high school exercise. You find immediately the exponents, A, B, and C. So if we plug them back, we get our formula. And this is a formula that you saw in the previous slide on the paper. And this is something that has been shown all over the place. Taylor derived it in this paper. He was not the only one. In the US, John von Neumann was working for the Americans. And you can see that the reports that they provided, so these top secret documents, they're dated only 3 days apart, which I find quite amusing. In the Soviet Union, Serov was also working on this. He wrote his first paper on that a little bit later. But he was also able to generalize some of the approximations of Taylor. And this quantity here, S of gamma for air, so gamma for air, if you consider it as a diatomic gas, is equal to 1.4. So this function is equal to 1.03. So it's very close to 1. Many people just ignore it, but that's not correct. And this is what people say Taylor did. If you look at his paper, you'll see that it's a 16-page paper, 15 of which he devotes to derive this function S of gamma. It's a really complicated exercise, so it's not trivial just to ignore it. He wrote his top secret document, but 1 year after the Trinity test, the pictures that I showed you before, they were declassified. And since they have timestamps and also a length scale, he realized now I can test my formula. I can check how good it is. And that is exactly what he did. He wrote a second paper with the same title, but part 2, he called it the atomic explosion of 1945. And I will show you what he did, because this is I find it a fascinating exercise for the kind of things that we do when we teach lab to our students, either mechanics or electromagnetism. When we have a power law, we always tell our students, always go to log space. The reason to go to take logs or to make our plots in a log-log scale is that when you have these powers, the exponents become just overall factors. If you measure the slope of your plot, you can derive these quantities, which is great. And if you do this, this equation that looks really complicated, so I'm interested on r as a function of t, becomes just the equation of a straight line. And we know exactly what the slope is. The slope should be equal to 1 if this formulation is correct. So this is what Taylor did. He took all those pictures and he measured the corresponding scale. And the plot shown here, I reproduce his data, and I also did the fit to this data. Notice that the data has no error bars, which shows that he was clearly a theorist. Data should always have error bars. You find that the slope is exactly 1, which is fantastic. That means his formulation was correct. But in addition, you get another piece of information, which is the quantity shown here, this 6.9, is the point where the line crosses the log of t equals 0. So this is the intercept. And if we look at back in our equation, the intercept is of course a constant that depends on the energy, this A0. In other words, we can invert this term here, solve for E0 in terms of the intercept. And since we know the density of air and we know the numerical value of S, we get the energy, and that's exactly what he did. He found the energy to be 16 kilotons. So this is 16,000 tons of TNT equivalent. The official yield was between 15 and 20, which shows that he did a really great job there. And that is what Taylor did. And I move now to the Beirut explosion. So last year, in August of 2020, we saw these terrifying images of videos from all over the place in which there was a building that blew up. It contains some material that should not be stored the way it was stored. I'm not going to talk about the security or safety details there. You see the fireball. You'll see also this condensation cloud. And one thing that I found interesting when I saw this, I was following this on Twitter basically live because people were posting this, is that there were so many videos from many angles. And I thought, if I have all the videos, if I could do some very basic image processing, I could extract some physics out of it. And that is exactly what I did. I just wrote a little Python script. I downloaded the videos. I got the screenshots. I immediately identified the timescale, which will be given by the frames per second of each of the recordings. Most of cell phone cameras use 30 frames per second, but one of the videos was a 60. Then I needed to know the length. I don't have length scale directly. I was thinking on using some sort of parallax, trying to use basic trigonometry for this, but the error bars were gigantic that I could not derive anything. So then it occurred to me that since there is this big building next to the explosion, I can use that as a reference. So I went online, I looked for the dimensions of this building, which is so-called the grain silos. So they store grain in this big building. And then now I got a scale. So now I can convert from pixels to meters, which is what I needed. The other thing is that all the videos are from different places in the city. So the angle is very important. I needed to calibrate everything with the line of sight, which means that I have to identify exactly from where the video was recorded. In order to do that, Google Maps was not enough. I found some satellite images of the city of Beirut. Then I used Google Maps and also Street View, and I started to go around the city until I was able to identify all these places. So there were many videos, around 20 videos, but I put a very strict selection criteria. So I wanted to make sure that I could identify the location properly. I wanted to have a clear view of the grain silos, so I could have this scale between pixels and distance. And I also wanted to see several steps in the evolution of the fireball. And by doing that, I was only able to satisfy all these criteria with 4 recordings. I used some Python to trying to extract automatically the size of the fireball. That was really challenging. In fact, a colleague of mine helped me out there. I was able at the end to extract 26 different pairs of R versus T. And with those, I can go and make a plot. So I did exactly what Taylor did. So I have again the log of time in the horizontal axis, 5/2 of the log of the radius, and they all fall along the same straight line, which honestly I was not expecting. And here's when I thought I should write this down, make it more professional. I did this only as a toy exercise on Twitter, But then I decided to go more professional with this. I look for the slope, and you can see in this plot here on the top left, we have the histogram for the slope is exactly 1, which is amazing. The other histogram shows me the distribution for the intercept, because as you know now, if you know the intercept, you can extract the energy. So once I got the intercept, in this case, I got 6.3 with corresponding uncertainty, I was able to use exactly the same formulas and derive the energy. So I found that the energy released by the Beirut explosion was around 2.3 terajoules or 0.6 kilotons. The error bars are quite large, but that's all I was able to do with the noisy data that I could get from cell phones, basically. As I said, I initially did this only as an exercise for me on Twitter. I shared it there, and then I decided to write it down. And the paper was published in February this year. Of course, I was far of being the only person doing this. Christoph Pilger, who works in the German Institute of Geophysics, he works with acoustic, hydroacoustic, and seismic detectors all over the world trying to identify nuclear tests. So he knew exactly how to get the energy out of this seismograph data and also from all these hydroacoustic and acoustic sensors. So he derived this within a day. He released this on the internet. And another group in the UK, led by Sam Rigby, called the Blast and Impact Dynamics Research Group in Sheffield. They're expert on explosions and how they affect materials, and they use a semi-empirical formula to fit their data, and they derive very similar energies. And then more people follow. There were many papers published later. The bar here in red is my result, and these are the others. They are shown here in chronological order. Other people use the crater. Other people use the damage produced in different windows at different distances to estimate the overpressure. So there were many techniques used, and they all agree. One of the things that happens when I wrote that paper was that I posted on the archive. I got many emails. Many experts wrote to me pointing out some mistakes that I made. So I learned in the process. I realized how ignorant I was about fluid dynamics in general. So I decided to go and become more serious. Sam Rigby, who was one of the papers that I showed you earlier, with him, we started interchanging emails and on Twitter, and we started collaborating. I would like to now show you a little bit more of the physics. It's going to be a little bit more intense, but I would like to show you what really is happening behind. So the picture that you see here is called the snowball test. So this was a huge explosion that took place in Canada. So this was a military exercise. Just to get you an idea, on the bottom left here, there is a truck. So you can see how big this thing is. So what you see here in white is the fireball. The shock wave is not that obvious, but if you look carefully, you'll see that there is some distortion in the air. And this happens again because at the shock front, the density, the pressure, they all change so dramatically that they will modify the index of refraction. And that's why they produce this optical distortion. The white stripes that you see behind, these are rockets that they launch all the time, so they can see the interaction or the passing of the shock wave. So this is why usually if you see any videos of nuclear tests, you will also see these white stripes or sometimes they're even crossing, just they can see how the shock wave interacts. This is another similar test. This is an American test in Hawaii. Again, almost 500 tons of TNT. You can see the shock wave also there. The main distortion is visible with the horizon of the ocean. There's a battleship there, and there are a couple of observation balloons on the sky. And in fact, the picture here on the left is exactly the same explosion, most likely taken from one of those balloons. There is a second battleship that we don't see on the first picture. On the right, we see the shock wave in the air because we see the distortion. In the second picture on the left, we don't see that, but we can see where the shockwave is going at that time because this is the point where it makes contact with the water and also with the ground on the left. This thing is growing as a hemisphere. So the goal of this collaboration that I started with Sam Rigby was, let's try to characterize this properly, because we were using Taylor's formula, but Taylor's formula makes several assumptions. Some of them might not be valid when we make observations. So we wanted to have a generalization of that. And the goal was, again, just trying to have a formula that tells us, given position versus time observations, we can derive the energy of the explosion. So there are codes that will do this for you. So we don't claim to be the first people to do that, but we wanted to have a more systematic way to see this, and even do it at a scale that any physics student, for example, could follow. So this is the analysis. We consider a sphere. This is in free air, so this will be completely spherical. We take a volume of a radius r around the center of the explosion. So here the explosion has not happened yet. So this is what I call it before. Pressure and density are the same inside and outside. And we can calculate the total energy enclosed in this sphere. The energy will be the energy, the potential energy in this explosive, plus the thermal energy in this volume. So this P0 over gamma minus 1 is just the energy density that you get for an ideal gas. So we integrate on the volume and we get the energy. After the explosion takes place, we're going to consider again the same volume, so the same radius, but now there is a different pressure, it's a different density, and now the gas inside is moving. So there is a velocity u. In this case, the energy will be the kinetic energy of the gas, which is the first term, and the thermal energy of the gas, which is the second term. Now, the problem is that we cannot directly integrate the right-hand side, because these quantities, rho, u, and p, they depend on the radius, but they also depend on time. So it's way more complicated. We need to find a way to find these functions first. And for that, we go to fluid dynamics. It's a nonlinear system of partial differential equations. So a lot of fun to play with this. And what we would like to do is solve these equations. If you're not familiar with fluids, this big D here, this derivative here, is a so-called hydrodynamic derivative. It has many other names. It's also called the material derivative or the convective derivative. And what we are seeing, these three equations, are just, the first one is just Newton's second law. The second is the continuity equation, so mass is conserved. And the third one is just the equation of state. So this is how density and pressure are related. Just need to solve these equations and plug them back here for the energy. And we're going to use these Rankine-Hugoniot boundary conditions to solve the system. Now, in order to solve this, I wanted to follow what Taylor had done, but again, he made many assumptions. So one trick is we introduce a variable that characterizes the radius. So eta is just the radial coordinate divided by the radius of the sphere, which is the chalk that will vary. So this eta goes from 0 to 1. So we have dimensionless quantities. And I will introduce a quantity called lambda. Lambda is the inverse of the square of the Mach number. Just to remind you, the Mach number is just the speed in units of the speed of sound. It's only that. It's only to have the speed in dimensionless units. In the Taylor paper, this quantity doesn't exist directly because it's equal to 0. That means that the shock is moving really, really fast. In other words, Taylor's approach is only valid at the beginning of the explosion. And for the other quantities, the speed, the density, and the pressure, I will introduce these dimensionless functions. So for the speed, I will introduce phi. For the ratio of densities, I will introduce psi. And for the ratio of pressures, I introduce this function called f. So I need to find these three quantities. Let me remind you the formula of conservation of energy. This is what I showed you in the previous slide. And if I replace, I will do some little algebra here just for you to follow, so I don't give you the final result as magic. The only thing that I did here, I replaced these dimensionless functions. This integral is just a number. So I will just call it k of lambda. It depends on lambda, but it's just a number. And on the left, I divide it everywhere by p0 over r cubed. And I will just rename a few things. I introduce a new coordinate for distance. Call it z, which is just the distance or the size of the shock wave in terms of this r0, which is just the energy divided by the pressure to the 1/3 power. So it's just we can have completely dimensionless variables. So z tells me the size of the shock wave in dimensionless units. So conservation of energy is given by this very simple looking expression. It is ugly because we don't know what k is, but we're going to get there. And now when I transform coordinates, if you remember from calculus, you need to use the Jacobian of your transformation and all these kind of tricks. And there is a function that appears everywhere. I call this function zeta. So this zeta basically quantifies how the shock is slowing down as it propagates. Once again, in the Taylor case, this is moving really fast and this function doesn't appear. In our case, we want to know how the shock wave decays. And that's why we're going to need this function zeta. If we combine these two, it's very easy to show that they are related by this differential equation. So I call this the blast energy relation, and it's the most important thing that I wanted to show here. So if there is one thing you wanna check out here is that we can relate the conservation of energy with the decay of the shock wave by this formula. Now, we don't know what zeta is, and we don't know what K is. And that's too bad, because we would like to know that in order to solve the system. One of the things that you can derive directly from here is the boundary conditions of zeta. You can show that if lambda is equal to 0, zeta must be equal to 1 by consistency of this equation. And when lambda is equal to 1, zeta must be equal to 0, again, by consistency. That's the only thing we know. Now we will need to find a way to solve for this. And here's when all these very advanced fluid dynamics codes allow you to find. But I wanted to get something not just numerical. I wanted to get an analytical expression. So here I thought, which one is the simplest function that satisfies these two boundary conditions? And that function is what I call the Blasi-K approximation. It's just 1 minus lambda. Satisfy those two conditions immediately, doesn't have any free parameters, is the simplest thing you can write. I understand that it's just an approximation because I did not derive this from any first principle. It's just a guess. If I plug this guess back to the definition, I get a differential equation now for lambda in terms of z, basically how the shock will propagate. This differential equation is nonlinear. In general physics, we're wired to stay away from nonlinear equations, but it happens that this is a very special nonlinear equation. It's of the Bernoulli type, and this can be solved very easily. So you can solve it in 3 lines with pen and paper. The solution, I just wrote it here. So we have now how this lambda quantity that I introduced earlier, that tells you about the speed of the shock wave, changes with position. We don't know yet what K0 is, but we're going to get there. Once again, the definition of lambda is the inverse of the square of the shock wave speed. So if we integrate this, we can find a relation between position and time. Since I introduced already some dimensionless distance called z, I will introduce a dimensionless time that I call tau. You construct a dimensionless quantity in time by multiplying by velocity and divided by distance again. And then you can write down a formula that tells you what time is in terms of velocity. So you just need to integrate. And if you integrate that function, you find your relationship between position and time. So it's not a final analytical expression. This still has to be integrated numerically. But this is something that you can do in 2 lines of code. This is the expression I was looking for. Let me remind you what K was. K was this ugly function, this integration of these functions that we still don't know. But we find that we only need K at lambda equals 0. We don't need it everywhere. And that means that we can solve this system. We need to solve a set of differential equations. These are again, the conservation of momentum, conservation of mass, and the equation of state. They look ugly. It took me a full weekend to solve these equations, but it was a lot of fun. I will not spend time on how to solve this. It's just a set of polynomials or ugly looking polynomials of eta, which is this radial coordinate, and gamma, which is the heat capacity ratio, which is equal to 1.4. So it's a number. We know what it is. And all these exponents, kappa 1 to 4, are ugly functions of gamma. So we know everything here. That means we can plug these functions back to this integral and find what K0 is, which happens to be just 7.86. And that's brilliant because now we can plug this number back here and we have the relation we were looking for. In other words, just to remind you the goal, we wanted to characterize how the shock wave will evolve just in terms of position versus time. And that is exactly what we have found here. And now I would like to show you how to use it. So once again, some expression. One thing we would like to make sure is that the solution by Taylor, Sedov, and von Neumann is contained in our solution. As I mentioned before, this so-called strong shock limit is what happens in the early stages of the explosion. That means short distance, In other words, the 1 is negligible because z is small. So if you take that limit, what you find is that this expression can be integrated completely analytically. And what you find is this expression, just to compare with the original set of Taylor von Neumann blast wave, I convert that back into the original function. So instead of z, I will use r, and instead of tau, I'll switch back to t. And what we find is this formula. And now this will look familiar. It's exactly the same as the formula that Taylor derived. The numerical value in front is 1.02. For him was 1.03. So I can live with that. We know then for sure that the Taylor solution is a subset or is a limit of our expression. In the other limit, when we are really far, that means that z is very large, very far from the explosion, one thing that we expect is that the shock wave will slow down until it reaches the speed of sound. So it decays into an acoustic wave. And if you take that approximation in the expression above, means that this second term in the integration is negligible, and the integration becomes trivial. And what you find is that the shock wave just propagates at a constant speed. And that speed is exactly the speed of sound, which is perfect. That means we know the two limits are satisfied in the short distance and in the long distance. And this plot here has a log of z in the vertical axis and log of tau in the horizontal axis. The two straight lines that you see are, first is the strong shock limit and the acoustic wave. And we see how this function transitions beautifully from one solution to the other, which is exactly what we wanted to find. Now, what about data? Let's put data on this plot and see how this looks like. I switched back to the Trinity test. As I mentioned, been obsessed with the Trinity test since I was a kid. So I wanted to see how this looked like in the plot. A few things that we see. First, we have our prediction. So this is the red line. The two straight lines are, again, the acoustic wave and the strong shock limit. There's also a horizontal line here denoted Z upper. This is the point where we found that the shock wave approximation start breaking down. That means it's only valid below that dashed line. The circles in blue shown here are the data from JMAC. These are the pictures that I showed you earlier. And everything, of course, fits in the region where the strong shock is valid. But you also see that I have a few data points really far away. Again, this is a log scale. So these are many kilometers away from the explosion. This data I could not find directly, but I had the following idea. If you have read enough about the Manhattan Project, you will know that General Groves ordered everyone who attended the Trinity test to write down a one-pager indicating what they saw. So a description of the test. If you read the military personnel writing down things, they only talk about politics, how the world would be different, and all these kind of things. But when you read the documents from the scientists, they were all making measurements. They were all with a clock. They were timing the blast wave, which is exactly what I expected. I took a few of them. Many people are probably familiar with the document that Fermi wrote, because during the explosion, he took a piece of paper and teared it apart into pieces of paper. He could feel the shock wave coming. He released all the pieces of paper, and just by seeing how far they move, he was able to estimate the energy. That was classic Fermi. But there were many others. So in the bunker with Oppenheimer, there was a measurement. Vicky Weisskopf was in a different position, but same distance as Fermi. Ernest Lawrence was further away. He didn't want it to be too close. Elizabeth Graves, that was interesting. She was one of the pioneers on the development of neutron detectors. She developed most of the detectors used by Fermi in the Chicago pile. So the first nuclear reactor uses detectors created by Graves. And she developed a whole set of gamma radiation detection systems for the Trinity test. But at the time of the test, she was pregnant. So she decided to be as far as possible, just in case. She was about 50 kilometers away. Using radio, she was able to tell t equals zeros, and she was timing the shockwave as well. So this is where I got this data. I'm really proud of getting those numbers. And we see that this works. Once we had this, we decided to combine our data sets. So as I mentioned, Sam Rigby, he had already with his team a bigger data set than mine, in fact. We put them together, and we can now see the whole evolution of the shockwave of the Beirut explosion from the early stages, from just the fireball, But later, the fireball is not that reliable. You need to look at the location of the shock front. Using this method, the energy of the Beirut explosion was around 514 tons of TNT equivalent. In this plot, I also have another line here. This is the so-called CONVEP. This is a standard set of measurements all the way from the 80s using blast engineering. So I included that just for completeness. Sam Rigby and his team, University of Sheffield, they have a site where they literally blow up stuff. So they experiment with different kind of explosives. And this data is a data set that he shared for this project. It's called P4. This is the British name for so-called C4 in the US. It's the same compound. These are explosions using 100 grams and 300 grams of this explosive. They measure at different distances. They have sensors all over the place. So these look like tiny explosions, but they're big bangs. And one thing that we see here is that the blue dots deviate from our curve. I also included an extra line called Z low. And this is because this is a chemical explosion. It's not a nuclear explosion. And I didn't talk about this, but there's not only an upper bound for the Taylor solution to work, there's also a lower bound. And this is when the size of the explosive becomes too large compared to the energy that is released. And we see the deviation in these blue circles. Included that just to show that that is in fact the case. So this is interesting. The Sedot-Taylor von Neumann expression works only in a very narrow region. And this for us was very important because many people use that expression for any explosion, and you cannot do that. You have to be very careful. Again, same plot, but this is very large scale explosions. I already showed you the picture of Snowball, almost 500 tons of TNT. Prayer Flat was very similar. This is another test in the green circles, 90 tons of TNT. And again, we see the deviation at the point where we expected. Here, literally the big guns. On the left, these are kiloton nuclear tests. This is a collection of different nuclear tests in the scale of a few kilotons. On the right, you have the equivalent, but these are thermonuclear tests. So these are all megaton explosions. A few of them are quite noisy. I spent time between Christmas and New Year's last year extracting this data. It was not available directly. I read literally a dozen of declassified documents, extracting each number one by one, but really happy to see the result. Here's something that I commented earlier. I mentioned it to Felipe. It happens that in plasma physics, people also create small shock waves. They basically shoot a powerful laser or some concentrated energy with a laser on a material, and they can create spherical shock waves. And they use a second laser to do high precision measurements of position and time. I looked for one of these very old papers. I extracted the data, so it's shown here in purple. This is what I denoted here as laser-induced shockwave. This is only a few hundred millijoules of energy, but they follow exactly the same curve. I find that fascinating to be able to put a few millijoules of energy from a laser in the same plot with nuclear explosions. And this is the nice thing about these coordinates. This is why we introduce these coordinates, so we can visualize all types of explosions in the same plot. And this is my last plot. Once we had this, one thing that Sam and I decided was what can be the grand finale of the paper. We thought, let's consider a bunch of explosions of different energies. So in this plot, we have tons of TNT. So we start with 10 tons of TNT all the way to tens of megatons. So we know about these explosions. We found this data, and we fit this data to our curve. The fit parameter was the energy released, and we can compare that to the official yield of those explosions. So the diagonal line here shows the perfect agreement between the fit and the actual measurements. And we see that all the explosions that we try, they all fall very, very close around this straight line. So we were extremely happy with the result. Some of the explosions you might be familiar with, the Snowball I showed you earlier. The Grabble test, if you're familiar with nuclear tests, is very famous because it was a new uranium bomb that you can shoot with a cannon. So if you Google for the atomic cannon, you will find a really interesting video of that. And Castle Bravo, of course, is that monster thermonuclear explosion that went terribly wrong because they forgot to consider that the lithium bombarded with energetic neutrons will make extra tritium. So the weapon happens to have way more fuel than expected. That's why Castle Bravo is well known. We were able to describe the shockwave produced by an explosion. This is in free air, so we assume it's completely spherical. And we can see now we have an expression that tells us how it transitions from the strong shock, the early stages, to the acoustic wave in the far distance. This is an approximation because we use an ansatz for the decay of the Mach number of the shock front. But this allows us to get these analytical expressions, which allows us to solve this complicated set of equations. We validated the results using explosions of all type, chemical, nuclear, and thermonuclear. And in the paper, we outline how to use this in order to use it in the future. So if there is any new explosion in which there is a video, if you can measure position versus time, you can use this method to work backward and estimate the energy. Thank you.
Thank you very much, Jorge. Very nice talk. An example of how physicists, we are always thinking about physical processes and the power of scaling. We have time for questions from the audience.
Hola, Jorge. Well, I'm fascinated with the talk. I mean, it's one of the areas I like the most. So it was like music to my ears. Congratulations for that.
Thank you.
I'm concerned. I haven't heard before about the chemical explosions and the relative effect on the effect on the size of the explosive with the expansion wave. As I heard, you mentioned that given that the chemical is typically larger than a point-like explosion, the curve deviates from the set of Taylor blast wave kinematics.
Yes.
You shown in one of the graph there was a straight line. I guess it was from the chemical explosions. Is there another analytical expression, or maybe numerical expression, for that curve depending on the size of the chemical or the explosive?
These are the chemical explosions.
The
ConVep. The ConVep is a data set that is used in blast engineering. You can imagine how many explosions the military have done, and they measure everything. So this is not only a data set, there is even a web interface in which you can select the properties of the explosion. You can select the type of explosive you want and the amount of the explosive that you want. So you can use TNT, you can use C4, etc. The curve that we see here is, in fact, you can say it's experimental data. So I show it as a curve, but it's in fact experimental data. One thing that some people do, and this is exactly what Rigby and company did for their paper on the Beirut explosion, you can select ranges in which you can use or you can fit some semi-empirical formula. And these semi-empirical formulas are only valid in regions. Something that you will find, for example, is they will say from a few centimeters to a few meters scaled by the amount of the explosive that you use. This is the formula you have to use. From that point to another point, it's like a piecewise function that they define. And that is because there is no analytical formula that will do that for you. This is one of the mistakes that, in fact, I made in my first paper. So I would like to acknowledge that. I included in the paper that was a mistake. It was corrected by the referees, in fact. And the same happened in the Beirut explosion. In the theory that I use, I'm using a spherical explosion, but the Beirut explosion happened at ground level. So it was a spherical explosion. With laser-induced shockwaves, something very similar happens. You have a plate, and then you shoot a laser, and then the shockwave will propagate as a hemisphere initially. So you cannot use the spherical formulas. But there is an easy trick. What happens is that the energy is produced in all directions, but if there is a surface, the energy going down, so in the lower hemisphere that doesn't exist, gets reflected. So what happens is at the end you get an enhanced explosion. So you will see something that looks like twice the energy only because of this reflection effect. I'm assuming a perfect reflection. So you need to multiply by 2, or the energy that you get, you need to divide it by 2, which is the equivalent. When I did this originally, this laser-induced shockwave, it did not match the straight line. I was curious to see what happened. And then I realized that I forgot to divide by 2 and immediately worked. In the
Yeah.
case of the Beirut explosion, it's not exactly 2 because you don't have a perfect reflector. The ground, actually, there was even a crater. The recommendation that I got from the referees on that paper was that the standard using in blast engineering is to use 1.8 instead of 2. So the idea is that around 20% of the energy is lost in the form of noise, destruction of the ground, the crater, etc. So at the end, the energy that I got initially in the paper was close to 1 kiloton, but then I have to scale it down by a factor 1.8, and it got around 600 or 550. So yeah, that's a very important point.
Outstanding. Thank you, Jorge. Te pasaste.
There is a question by Armin.
I did not say anything about how the energy is transferred from the explosive, whatever that is, to the air. For that, there are extensive studies. I mean, one of my heroes is Hans Bethe. He was one of the people who developed the first calculations of blast weights. There are a lot of things that you need to consider in the nuclear case, for example. As you know, there is a burst of X-rays. X-rays will, for example, ionize the air, and there is a lot of energy that gets lost via ionization. This is what produces the famous electromagnetic pulse of nuclear explosions and all these kind of things. In the chemical case, that doesn't happen. Also, in the nuclear case, the temperatures are way higher, so that also induce some ionization that has to be taken into account. So there are many processes that I completely ignored. I assume that the energy gets released instantaneously, just like Taylor and company. There is a document available for free on the internet. It's called Blast Waves by von Neumann, Bethe, and also Klaus Fuchs. In case you know about nuclear history, you know that Klaus Fuchs was a Soviet spy in Los Alamos, and he was one of the one writing the codes to solve precisely this problem.
I have a question. What if you change the assumption about seat or as a function of lambda? You choose
oh yeah,
one
I know what you
minus
mean.
lambda, but it could be y minus lambda to a power.
Yes, honest answer. Things will get really complicated because if you have another function of lambda here, as you said, you just need another function that satisfies the boundary conditions. I use the simplest linear expression, but you could have a quadratic form. What would happen there is you will most likely get a more accurate description of the transition from the strong shock to the acoustic curve. So these two straight lines, this transition will get better. In fact, in the data that I showed, there are a few cases in which this part of the curve, the data is a little bit away from our curve. So what would happen is you'll get a better approximation.
Any other questions?
Well, Jorge, thank you very much for this nice talk. I have two questions. One is the first one is some kind of cultural or historical question.
Yeah.
I want to know your comment about that. It is supposed that explosion physics is one of the most studied subjects in physics for obvious reason, right? So yes. My question is how it is possible to found a new equation or some kind of interpretation of this all this kind of explosion in this huge range of energy. So that result are already classified or this is totally new? What
you have a good point.
About?
So basically, how is that we are in 2021 and just now we're learning about this new formula? I would not phrase it like that because I don't want to claim that we have found something completely new. If you use numerical calculations, you will get much better results. That's the truth. People stick to those numerical solutions of those advanced codes of fluid dynamics that do not require so many assumptions. They can put more realistic effects in these codes and then just let them run with big computers. I think they will be way more reliable than the expression that we have. Then why are we doing this in the first place? In this plot, we have the chemical explosions. Fortunately, we don't get nuclear explosions anymore, and let's hope that remains like that. But unfortunately, we get a lot of chemical explosions. And one thing that happens is that people that know about this story of Taylor and company, just go rush, take that formula, and then do some estimates. How can we identify properly the range in which this Taylor formula is valid? How can we make sure that we're not using it in a region that is no longer valid because some of the assumptions break down? We wanted to have something very, very simple that we can point to engineering students or people doing this in a more not professional way as someone in the military, for example. So we can tell them, be careful because this expression is only valid in this regime, in this range. If you're out of this range, you can no longer use the formula or you cannot rely on the results. That was one of the practical reasons we wanted to have as many analytical expressions as possible. But you're completely right. There are way more advanced ways, fancy ways to do this, and governments have their own formulas, I guess, most likely advanced codes.
No, but for us physicists, this is fantastic. Yeah, and
it's a fun exercise. Yes.
Yeah, it's just a short question. It's about how can use this approach for shock wave, for example, in solid. It's just a matter, in quotation, just a matter of to change the equation of state or that you put in the slide 21 instead of the thermal energy of ideal gas, put the corresponding equation of state for the kind of solid?
That's a good question. I did not think about solids. I think at some point I was wondering about water because, as you know, there are many nuclear tests that happen underwater. I am pretty sure that it's not only just changing the density, for example, or the equation of state. If you have a solid, I'm pretty sure that you will have different kinds of waves that will propagate. Just like a seismic waves, you know, that you have the P waves, the S waves. I think you will have to consider these other effects as well. Honestly, did not think about this. I'm not sure about the details. I would be surprised that it's as simple as just changing the equation of state. I will bet that there is another complication.
Great, thank you.
I was really hoping that somebody would ask about this because there was a lot of confusion in the media regarding this cloud around the explosion. Most of the articles that I read online refer to this white cloud as a mushroom cloud, which is incorrect. Yes, there was a mushroom cloud, and there was also this hemispherical cloud around the explosion, but these are two different phenomena. The three images here on the left correspond to three different views of the same explosion in Beirut. In all of them, you can see this white hemispherical shape around the explosion. And the one on the right corresponds to one of the early nuclear tests in the Pacific. You can see the similarities between the two and why many people got confused. There was even the speculation that the Beirut explosion was in fact a nuclear explosion. It was not. It just happens that this phenomenon can occur in both nuclear or chemical explosions, and in fact has nothing to do with the type of explosion and is more related to the atmospherical conditions. So once again, just to be clear, this white cloud around the explosion is not a mushroom cloud. It is called a Wilson cloud or simply condensation cloud. And as the name indicates, this corresponds to droplets that form around the explosion due to the differences in pressure, temperature, etc. One thing that can be seen in all the images is a point of contact between the shock wave and the surface of the water. And we see that the white cloud is in fact behind this. The reason for that is that when we have a compression of the air in this case, this compression will be followed by a rarefaction. This is the point in which the pressure drops very quickly. In the front of the shock, the pressure increases dramatically, and right behind it, it will be followed by this region of low pressure. If there is a high level of moisture in the atmosphere, these changes in pressure and temperature will lead to the formation of droplets, and these droplets constitute the Wilson cloud. The Wilson cloud is also short-lived because as the shock wave expands, the intensity of these pressure differences will decrease. It should be noticed that this phenomenon is not unique to explosions. In fact, it's something that you can see every time there is, for example, a rocket launch. You might have also seen images like the one here on the bottom left. Here, another big warning. This has nothing to do with the speed of sound. This is only a consequence of pressure differences. In fact, this phenomenon occurs at transonic velocities. That means the fighter doesn't need to be moving at the speed of sound or above the speed of sound to produce this cone. So no, this is not a sonic boom. The picture in the middle shows in fact a commercial plane. These planes are not moving above the speed of sound at all. In fact, this plane is about to land. So once again, this phenomenon is a consequence of pressure differences and combination with the proper atmospheric conditions. I call it a big warning because many people refer to this phenomenon as a sonic boom. It is not. It is not a sonic boom. It is not a sonic boom of a fast-moving jet. It is not a sonic boom produced by a rocket. It is just a condensation cloud. I will refer to one of my favorite threads on Twitter by Chris Combs. He put together a collection of tweets in which he explains step by step how these condensation cones or vapor cones are produced, which I highly recommend and I repost all the time. But what about the mushroom cloud? This is a picture of the Beirut explosion. This is, in fact, a mushroom cloud. This is an image a few seconds after the explosion, where the Wilson cloud, in fact, already dissipated. We see precisely what is shown in this diagram. Air that has been heated will rise very quickly due to convection. The hot airs will start circulating and the gas will expand. That is what creates the head of the mushroom. And these mushroom clouds are very common. Every time there is a release of hot gases, they will move up very quickly and the standard mushroom cloud will form. The reason for this is known as the Rayleigh-Taylor stability. Yeah, Taylor, it's the same Taylor. At the end of the 19th century, Lord Rayleigh showed that when you have two fluids of different densities, one on top of each other, they would lead to this instability. And later Taylor showed that the same could happen if you shoot a low density fluid into a high density fluid. And this is exactly what happens when we have gases that are heat up very quickly. The density will decrease and they will start going up in the air. So it's the same phenomenon, but it's basically upside down. This is the phenomenon behind mushroom clouds.
Okay, thank you again, Jorge, for this beautiful talk. Bye.
Yeah, thanks again.
Have a nice.
Bye.
Chao, gracias.
Bye.
Ciao.